Hello, welcome to the show. So today we're going to be looking at the Jacobian Matrix, or in layman's terms, how you go from a Cartesian coordinate system to any other arbitrary coordinate system, provided you know the other coordinate system's function with a relation to the Cartesian coordinate system. Okay, wonderful. The best way to do this, I think, would be to do it generically, then apply an example. The example we're working with is spherical, polar spherical coordinates, and we'll start that in a bit, but let's look at some of the basics to start with. When integrating a three-dimensional function in Cartesian coordinates, you have our z, we've got y here, and x. Okay, and when we integrate them, we simply have three integrals, give you a volume, 1 dimension, 2 dimension, 3 dimension, and we have our function of x, y, and z. And then we have our dv, which is big V, okay? In the case of Cartesian, hopefully you should know it's just dx, dy, dz, but when we change up coordinate systems, it's not quite that simple. And the way we find it out is by using the Jacobian. Now, grab some more chalk. What we're doing is we're getting a new system. A new system where we've got, instead of x, y, and z, we've got u, v, and w, let's say. And it's the question of changing this into another three-dimensional integral with u, v, and w. Okay? The dv's have to change, and that's what we're looking at today, how we find the dv's. Okay, so let's lay out a few definitions and a few parameters and then get cracking. So the first thing you have to kind of lay out, and hopefully most of the time the question will give you this, is saying that x, your x coordinate system, as a function of u, v, and w. When we give an example, hopefully what this means should become a bit clearer. Same for y, and indeed z. All this is saying is that you can convert from Cartesian to this new coordinate system, which you can, which you should be able to do. Let's crack out our example, which is spherical, polar spherical, and this should be taken as read, this should be known. If not, we could go through it if you want. And it's just a case of knowing how to go from one to the other. Again, yeah, if you're not happy with how we work this out, or where we got it from, if you like, then by all means, chuck us an email and we can go through it. But hopefully you should recognise these as the relationships between Cartesian, x, y, and z, to spherical polar, r, theta, and phi. Okay, so this is all I mean. When we're taking x in terms of u, v, and w, we're just taking x in terms of three new parameters. Cool. It should be made clear that I'm using a few conventions and a few assumptions, which I'll just outlay now, because some textbooks do it slightly differently. What we're going for here is that the r is just the distance from the origin. Yeah? R is just distance from origin. Okay? Theta is the downward angle from the vertical, from the z-axis, if you like. Okay, so theta 0, so increasing until we get to 90 degrees, and phi is the angle going round the coordinate system. So here, that's phi. Okay, and this makes sense because when theta is 90, we've got no z, there's no height on the thing, and when theta is 90, cos theta equals 0. So that's all jolly good. Okay. So that's the kind of base. And not only that, we need to lay out a couple more definitions, which is dv. That thing we put after the function before we triple integrate is simply the dot product of b. Try that again. Is simply the dot product of a with the cross product of b and c. What are B and C and A, I hear you say? Well, they're just this. dr over du du. Couple of points here worth getting our heads around. Firstly, this R, not the same, two different R's. The R here is the R vector, and the R vector is hopefully recognisable as this one. The R vector is just x, y, and z. Cool. And we've got partial derivatives inside the brackets and a full derivative outside. Important in your notes, not too important for understanding. It should come through in the maths, and it'll be okay. I wouldn't worry too much about that. Okay, so that's our A, and B and C. We simply don't use U, we use V and W instead. So let's get those down over V, remembering per curly D then, and C. Oh, there we go, that's dr over dw. And that bottom one can be seen there. Yeah, so these are just A, B, and C. That's our dv, and these are Cartesian to polar. This is all you need to calculate the Jacobian matrix, which we'll do now. Okay, so I've written these vectors in terms of u, v, and w, so they're generic. As we're going to work through our spherical example, let's change them up. Let's actually put in our values. So u, our first new parameter, that's going to be r. Remember, a different r to this one. Okay, v, let's call that one phi. And our third and final parameter, w, is just going to be theta. Okay, and hopefully we can start to see where this is going. Okay, smashing. Hopefully we've got those down. So now what we're going to do is we're going to do the differentials for A, B, and C, slap them in there, bang, out comes the triple integral ending. So yeah, let's move you guys across a little bit. Awesome. Okay, all we need to do now, as I was saying, is just work out what A, B, and C are, and then we can find dv. Nice and easy. Okay, cool. So let's do A first. Okay, so as I said, this R, not the same as this R, it's actually the vector x, y, and z. So we can extend the A vector down. And we actually get dx over dr, dy over dr, and dz. We can still see that just about over dr. Cool. And we times all of these by big dr like this. Okay, so this is where we have to do some derivatives. So dx over r, using the definitions we had earlier, which hopefully you just still have somewhere on your person, just gives us sine theta cos phi. Okay, dy over dr just gives us sine theta sine phi, and z we just have cos theta. Okay, and we put a dr at the end, and this is just our A vector. Okay, so this over here is our A vector, and yeah. Okay, cool. I'm going to write this down over here, so we've got it for a second. I'll be back in a tick. Hold on. Give you a chance to copy it down as well. Okay, smashing. Let's move on to the B one, and let's change up colours, because that's going to be fun. Okay, so B now, we've still got x, y, and z, but instead of r at the bottom, we are using phi. Okay. That's fine. Okay, and these change as well, as you'd expect. So, when we differentiate x with respect to phi, we get minus r sine theta sine phi. All we've done is change cos phi to minus sine phi. When we differentiate y with respect to phi, we get minus r. No, we don't. Sorry, we get plus r sine theta cos phi. It's not negative because when we differentiate sine, we just get positive cos. And z with respect to phi is quite pleasingly 0 because there's no phi dependency in the z term. And again, I'll just pop over here and write that down. So minus r sine 0, and that's d. Yeah, cool, and that's d phi. That's the last thing I should have popped down here. That's now d phi. Okay, cool. So we've got that written down, we've got that locked in, if you like. And now let's do C. So the x, the y, and the z stay the same. All that changes is this phi changes for a theta. Okay, so when we have x and we differentiate it with respect to theta, we no longer get these. What in fact we get is r cos theta cos phi minus r, oh no, sorry, big fan of those minuses apparently, just get an r cos theta sine phi, and at the bottom, when you differentiate z with respect to theta, you get, here we go, minus z, minus r sine theta. Okay, so this is the differential of x with respect to theta, this is the differential of y with respect to theta, and this is the differential of z with respect to theta. And at the end, we have to times it by d theta. And I'll write that over here. R cos cos, R cos sine, minus R sine. Okay, cool. We have our three vectors, they're written up over there, we'll nip over there in a sec. All we've got to do is cross B and C, and then dot them with A, and there we should have our dv. Okay, let's pop over there and do that now. Hey, back onto the big board. Right, so we've got dv, and that equals A dot B cross C. Let's do B cross C first, as we should. And yeah, if you start with a cross product, look at some other videos, maybe go on Wolfram and check it out. We won't go through it too explicitly here because we're kind of powering through. But yeah, make sure you're following each step. Also, I should just say, I've replaced sine with just the letter S and cos with just the letter C. I hope that's all okay with everyone. Okay, wonderful stuff. Let's get cracking. B cross C. So we have minus r sine theta sine phi, r sine theta cos phi, and 0. And we're crossing that with r cos theta cos phi, r cos theta sine phi, and minus I sine theta. What you'll notice when I'm doing the cross products and the dot products, I'm going to be leaving out these d's. They apply to all of them in here because they're outside of the vector. And what we'll be doing at the very end of this dv is just be chucking dr, d theta, d phi at the end. I hope that's okay with everyone. I will remember to do it, don't worry. But if you're wondering where they've gone, they're in here and they'll be coming back in a little bit, just so it doesn't mess up the algebra too much, make it too messy. Smashing. Right, let's do the cross product of these guys. Okay, so to do the top, we get rid of this top one, and we go down here. So it's minus r squared sine squared theta cos phi, bang, 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 minus 0. Save some time. Okay, middle one, bang, dang, dang. So that is minus r squared sine. Yes? Yes, we're all good. No need to panic. Sine squared cos theta. So we've got to do the middle one. Yeah. Sine theta minus 0. Sorry. A little bit of a hang on about. Sort myself out. A little bit of a moment there. But yeah, it's minus r squared sine squared theta sine phi minus 0. And then we want to do the bottom one. We just get rid of that, and we do bang bang minus that. So minus r squared sine theta cos theta sine squared phi minus r squared sine theta cos squared phi. Okay, this is B cross C. And now hopefully we should be able to use some trigonometric identities, namely that sine squared plus cos squared equals 1. So I'll keep all these up. It'll be a little bit small down here, but I hope that's okay. So this down here is just the same as minus r squared sine theta cos theta sine squared phi plus cos squared phi. Can we just make sure we can see that? Yeah. Okay. So we're just putting it into brackets, and then this equals 1. Yeah? Sine squared plus cos squared equals 1. So we can actually get rid of that whole thing. Just go for the 1. And we can change this bottom line here from minus r squared sine theta cos theta. Okay, cool. So there's our b cross c, and what I want to do now is just dot that with the a, which should be fine, I hope. Yep, so I'm not going to go through it again too explicitly. I'll just get rid of the minus zeros. I'm just going to dot this with the a and then add it all together again. So I'm going to pop this. Actually, let's do the a up here. Let's do the a up here. Let's make it nice and simple. Okay. So again, this is our b cross c. Let's make that clear. And let's do a dotted with it. So we got our a up here. So let's dot the first two. We have minus r squared sine cubed theta cos squared phi. Adding to that, this one down here, which is minus r squared sine cubed theta sine squared phi, and then minusing it down to r squared sine theta cos squared theta. Okay, cool. I'm going to get rid of the BC because we've done all we need the B cross C. We've done all we need to do with that one, and it's time now just to simplify down, which is brilliant. First thing we can see, we can get rid of, let's look at this one first. Let's get rid of the minus r squared sine cubed theta. Okay, this really is just a case of cancelling. And then we've got cos squared phi plus sine squared phi. Let's chuck in this last term as well to make sure we're being consistent. That should be, oh no, that's fine. That should be theta as well. Brilliant. That there, that's just 1. So bye-bye to you two. Now we've got this guy doing quite well. Let's get rid of the minus r squared sine squared theta. Sine theta, we've got to square it for now, and we'll do sine squared theta plus cos squared theta. And again, that just equals 1, which leaves you with r squared sine theta. And because it's the Jacobian, we're going to be taking the modulus of that, which leaves you with r squared sine theta. And remembering to put in the dr, d phi, d theta, we have r dv. So, when you're integrating, not using a Cartesian system, when you're integrating using a polar spherical system, you know now that once you've converted the limits, once you've converted the function, the dv at the end is not simply dr, d phi, d theta. It is, in fact, r squared sine theta, dr, d phi, d theta.